Welcome back, and hi everybody. And thanks to Sebastian. He is accepting to share with us his knowledge for the second time. And we will discuss today board piles, construction and design. And just as a hint, the board piles are called in USA, I think they're called as drilled piers.
Drill shafts, yes.
We call it also caissons in Canada, and we call it board piles in Europe. And I don't know what is called in elsewhere.
Yes, that's a good point, Ahmed, because I was in South America last week and I call them caissons, right? Because caissons in the US and North America is also one of the names. But for example, in Colombia, caissons are understood as board piles, but when they are made by hand. If they are made by hand, they are called caissons. So yeah, so I think everywhere in the world it's a different terminology. But
So I'm welcoming you again, Sebastian. Thank
yes,
you for
sorry, I should
being.
say I didn't even say hi, correct?
Thank you
Yes,
for being with us again.
always.
I will not introduce you. I'll introduce you before, and people may go back and see our first recording, which was great and about slope stability and supporting slope stability by piles or micro piles. It's all yours now. Let's just start something, okay?
All right.
Thank you.
Well, thank you very much, Ahmed, and thanks again for the invitation. Uh, but yeah, no, it's always awesome to be here, and I always look forward to our talks. I think you make them extremely interesting, and we always have very healthy and constructive discussions that that really promote better understanding of things. So yeah, just to a small parenthesis, and as you said, we really recorded a very nice session last time on slope stabilization, and I also invite everyone to go and watch that one. But just like for those that didn't want it, just to kind of give a little brief of who I am. My name is Sebastian Lobo-Guerrero. I'm originally from Bogota, Colombia. I came to the States almost more than 20 years ago and did my master's and Ph.D. at the University of Pittsburgh. I've been working in consulting now for almost 18 years, doing mostly geotech for transportation industries. But I also teach at the University of Pittsburgh, and I like to do a lot of different training and educational activities with professional societies. So just to begin, those are a few pictures that explain what you are going to see in the next few slides. I'm extremely passionate for what I do, and same as you, Ahmed, I identify myself with the profession, and I have lived my life due to the profession, and the profession has given me everything I have, and it has taken me to every place that I've been. So these are a few pictures just growing up. On the right side is me at college when I started studying geotechnical engineering back in Colombia with some classmates. Same thing on the top right, visiting a construction site. That one is actually more than 25 years ago. On the left bottom is when I did my undergrad at the University de Los Andes in Colombia. And then the top left, it's a very special picture for me. It's 20 years old, as you can see, by the 2003. It was the first it was actually the second presentation I did in the US, but it was kind of like the first one that I feel more comfortable, and I kind of remember this one as very important. It was at MIT, at the Massachusetts Institute of Technology, which is the same place that Terzaghi went, and he basically teach for the first time in the US. So not that I'm trying to compare to him, but it's just cool to visit the places that obviously he passed by. So with that,
He
let me
will
just
be
go.
always inspiring
Yes, exactly. He will
all of the
always be.
geotechnical engineers. He's a
Yes,
very
and
special
and
case.
And a parenthesis, I'm reading right now this summer, I'm reading for the second time The Engineer as Artist by Dick Gottman, which is the biography of Terzaghi. And if someone can get hold to that book, you can buy it on the AC website. It's absolutely worth it. And you absolutely get inspired by reading his story and, how the profession that we have really started, right? So, but anyway, to begin with the presentation today, we're gonna talk about drill shafts, and we're gonna talk specifically for LRFD design. In the US, in particular, this LRFD design mostly is done with the AASHTO methodology and also the Federal Highway Administration. So let's start with design, right? And how the design is affected by the methodologies compared to what we used to call the allowable stress design or the factor of safety design. So just to begin, basic stuff, doing a drill shaft, what it consists is we drill a hole, right? And then we go to to a competent strata. Today, specifically, we're going to talk drill shafts in bedrock, but it's not that different from the drill shafts in soil. You make the hole. Once you have the hole, you put the reinforcement, you put the concrete, and then you have the element. The element is going to work in two basic capacities. One is end bearing, which is basically coming from the bottom, and side friction or skin friction, which is on the sides. So the story of the equation for the capacities started a long time ago, and we have really great gentlemen like Horvath and Kenny and Fred Kolhawi at Cornell University, and they developed different equations. And for the longest time, we were using a simplified equation for skin friction. But then in 2005, everything changed. LRFD was introduced to AASHTO in 1998. By 2005, that was already 7 years implemented. The equations shifted and became a little more strict. So what I'm looking on the screen right now as AASHTO 2012 and earlier, it's the basic equation that we have to calculate skin friction. I don't want to start like really going term by term into a lot of killing the mood for the presentation, but it's important to understand the variables that were involved. We were saying that it was 0.65 alpha E. The alpha term was basically a function of the jointing and the RQD and the of the material. PA is just a matter to put the units. So in this case was KSF. So the atmospheric pressure is 2.1 KSF, and then the really important part is the parentheses, which QU is the ultimate, is the unconfined compression of the rock specimen, divided again by PA to take the units out, and then a square root of that. So we used to do it like that with the unconfined compression of the rock, and then we also used to check with what is on the right side, which is just a function of the concrete. So F prime C is just the strength, is the unconfined compression of the concrete. So depending if the rock or the concrete control, you will always take the smallest one, right? And then typically for a 3000 PSI concrete, you were always limited to an ultimate skin friction of 19.7 KSF. That was the number that we talk, and we use for years. Obviously, we are doing LRFD. So LRFD consists that you take all your geotechnical resistance and you multiply by a number less than 1, right? That's your reduction factor. And then you take your loads and you multiply by a number greater than 1. So that's your load factor, right? And then the combination, the load factor divided by the resistance factor, it's pretty much equivalent to your factor of safety if you were designing with allowable stress design. So anyway, this is the equation that we were using until 2012. Then AASHTO 2014, which is based on the Federal Highway Administration Geotechnical Engineer Circular for drill shafts, which was produced in 2010. Down Brown and Associates, my good friend Down Brown being one of the main authors, they changed this and they simplified the equation and they went into a more empirical approach that was based, it was kind of going back to the beginning because it was based on the Horvath and Kenny equation from 1978. And what we are really saying is that the skin friction on a rock is the square root of the unconfined compression when it's expressed in TSF. So that equation that you see there, in reality, it's simpler than it looks. QU, again, is the unconfined compression. PA is just to convert to TSF. So you take the square root on TSF. And then the C value right now is being used as 1.0. And then
TSF or KSF? It's written KSF there.
So in this one is in KSF, but the original Horvath and Kenny equation was in TSF. So what you are doing with the PA, which is 2.1, right? It's just to convert your KSF into TSF. So when you calculate the square root, it's calculated for a TSF. And then once you get the result, you multiply again by 2.1 to go back into KSF. So it's just like a little math trick there. The important part is you just need to use it on KSF the way that it's written. But I guess the relevant part here is that this equation now gives you 30.3 KSF if you use a 3000 PSI concrete. So it basically, in a matter of 2 years or 4 years total, we change and we are saying that we are increasing, and this to me is crazy, we are increasing the skin friction by a factor of 1.5, right? So how can you do that? I mean, does that mean that everything that we did before, because I've been designing drill shafts for a long time, right? So does that mean that I over-design all the ones that I did before this code? And in reality, the answer is no. What happened is LRFD, as it advances, because you have load factors and resistance factors, you are optimizing your resistance factor. You are punishing less the areas that you have a lot of confidence, right? And you punish a lot the areas that you don't have confidence. With all the advancement in the last 20 years that we're going to go through today, you are able to do this. You are able to use a more aggressive design because you have way better control during the construction. And I promise this is the last equation that I show on the presentation, and then after that is all pictures. So the other big advancement that happened is that different codes, I mean, the AASHTO, either in 1998 and AASHTO 2005 and all the subsequent editions, 2012, 2015 and all that, they always say that you can combine the contribution by end bearing and the contribution by side friction, but they leave it up to you as designer. How do you combine those two? And that's not something easy to do because the main problem, as we all know, is that the stresses mobilize a different strain. On a side friction, you typically go to a peak condition when you have a displacement of about ½ inch. So when I have the surface of the rock and the concrete and they move about ½ inch, I go to peak strength. Once I move more than ½ inch, then it's going to continue moving, but it's going to go down into a residual state. It's kind of what I'm showing.
This one is for point resistance.
Correct. But I'm just illustrating this to show the relevance of the strain. So I know one is for point, one is for shear, but if you put the low displacement curve, you will see the red curve getting a ½ inch, and then going down into residual, while the end bearing, right? The end bearing never finalized to mobilize. Basically, it's very weird. It's very strange. I don't think any has documented a end bearing failure of a drill shaft on bedrock. So what happened is you increase the load and it just keeps increasing, but it starts kind of flattening. The curve starts flattening, but it never really goes and fails, right? It just, because of all the confinement that you have on a drill shaft for the end bearing condition. So then what happened is, the traditional equation for the end bearing is 2.5 the unconfined compression. And that is the easiest equation to demonstrate. But because what they were saying is if you have a competent rock, right, they doesn't have that many fractures. I can say that the rock mass behavior, it's similar to the core. Typically on rock mechanics, you never say that, right? Typically you say whatever property that I have for the rock mass, it's only a fraction of the property of the rock core. If you are looking elastic modulus, if you are looking strength, whatever you're looking, the rock mass, it's always weaker than the rock core because of the jointing and the bedding and all that. But if you have a very competent rock at depth and you assume that the rock mass it's as strong as the rock core, you can say that your ultimate strength, right, for bearing purposes is the unconfined compression. It's actually conservative because unconfined, as the name mentioned, it's not
still
confined.
It is unconfined.
Correct. So because it's still unconfined. So we used to do this equation by saying that it's 2.5. And the reason is because we used to use a factor of safety of 2.5. So if I take an ultimate end bearing of 2.5 times the unconfined and I divide by 2.5, I basically end up with the same as the test, right? So that was the traditional equation that was used when the rock was good. But then the problem was, yes, that is your strength, but that happened at a significant deformation, right? Now, that significant deformation was typically assumed to be, and this is an empirical rule, it was typically assumed as 4% of the diameter of the shaft. And I know it's even in a different plane because the diameter of the shaft is horizontal. The deformation we're talking for end bearing is vertical. But it was a rule of thumb that you say when you have a deformation, a vertical deformation of about 4% of the diameter, assume that is your ultimate for end bearing. So what a lot of these codes did, as the one in Pennsylvania that we use, is
in the traditional European approach, and generally even in the traditional foundation engineering, we assume the ultimate end bearing occurs at around 10% of the diameter.
Okay.
But this one, it's related to this is DM4.
Yes, correct. So this one is going a little conservative.
Do you know if it is the same as in AASHTO or not?
Yeah, so AASHTO doesn't really give you that particular equation. AASHTO just gives you the ultimate, and then it says that it's up to the designer how to combine the two. So what the state of Pennsylvania did with DM4 is that they put this equation.
You want to limit your ultimate to 4% of the diameter.
Correct. And then what Pennsylvania did is that they just did a proportion and said, okay, well, I'm going to make it easier. If I get to peak at a ½ inch on skin friction, I'm just going to assume a proportion at that deformation of the ultimate. So they basically said 0.5 inches divide by 4% of the socket. That gives me a proportion, right? Like a linear proportion. And then I just take a fraction of that ultimate. So if the
So,
ultimate is
so
2.5 QU,
you are assuming that at zero point 0.5 inches, your
mm-hmm,
skin friction is already um,
peak,
peaked.
correct. And then you just look the equivalent on end bearing and just take a fraction.
Now it's clear. Yeah, I
Yeah, and
understand.
typically that number typically end up being between 10 and 20%. Like that zero point 0.5 inches divided by 4% of the diameter. If you are using 4 or 5 feet diameter shafts or something like that, you will get something, I don't remember, but it's like between 10 and 20, right? So it end up being a small fraction. Now, the relevance of all this is that now you are combining everything. So not only you are going with a higher skin friction, but you are also incorporating and bearing, right? So
Yeah,
obviously the effect that all this
which
had.
makes sense, so that you have some contribution from the end bearing to the resistance, unlike
Mhm.
if you just design based on skin friction or something.
Correct. And that was like when I started my career and we were using the Ashton 98 code. The Ashton 98 code was actually just advising you to use one or the other. At that time, it was more like estimate your settlement. If your settlement is more than zero point 0.5 inches, only use end bearing. And if your settlement is less than zero point 0.5 inches, then just use skin friction. It was just one
Oh,
or the other. So as the time evolved, and this to me has been fascinating because also has been like the story of my career, right? We start becoming a little more aggressive thanks to LRFD because we distribute the uncertain and the risk, and we control the quality during construction. So by doing all this, we can go to these more aggressive equations. But this is extremely important. Like when I teach the class at Pitt, or for example, last week when I was teaching my class in Colombia, when you take the equations and you do an example, you will realize that the shaft now is it's basically with the new equations, it's about 1/3 of the length that with the old equations. So that immediately is like a red flag, right? Because like, so you are telling me that by changing these equations, now I can get away with a shaft that is only 1/3 of the old one. And obviously that represents a huge saving in cost. So that is extremely important. But then you also need to understand the caveat of all this. It's like, yes, but to use those equations, you have to be really careful what you're constructing. Now, before you were constructing shafts really without much quality control. So that's probably the reason why those equations were conservative, and everyone's fine with that. So what we're gonna talk today is like that construction process, right? And how do you guarantee that you can actually use the equations?
are you going to show the LRFD action and resistance equation later?
Well, I can describe it because basically it's the equations that we talked before, and then you multiply by
So
a
we're
resistance
not
factor.
going to that part
We're
today.
not going to that part today exactly, but I can tell you how you go because it's very simple. You have the
I just
equations.
want to ask you one question, if you don't mind. If
Absolutely.
if you have a couple of layers
Hmm.
and your shaft is going through these layers,
Hmm.
are you going to calculate the ultimate skin friction for each layer? Then you sum the total, then you apply the factor to reduce the resistance, or you go through each layer and apply different factors to decrease their resistances, then you cumulate the total factored resistances of these layers.
That's a great point. And typically on LRFD, the way that you do it is the first way. You add the contribution of the different layers, right? And then once you add all that resistance, then is your ultimate resistance adding everything. Then you apply the resistance factor. Typically, that resistance factor is about 0.55. So you calculate the ultimate of everything, the ultimate load and resistance, and then you multiply by 0.55. Now, the load itself, depending if it's dead load or what kind of load, it's multiplied by a load factor. So the typical one is, for example, 1.5 is a typical factor. You also have like the concrete could be 135, live surcharge could be 1.75. Now, another point that is extremely important on what you just said, Ahmed, I'm very glad that you wrote it, is you typically also have constraints. If I'm not all the rock is the same, right? So if I'm going with my shaft between sandstone and claystone and sandstone,
Maybe
tip,
sand, maybe clay.
maybe
Uh,
clay, exactly. So
is
typically you
yeah.
neglect all that. I mean, there are a few rules of thumb. If you have different rock, different bedrock units, and some of the units have an unconfined compression strength that is less than 20% of the strong one, you neglect the weak ones. Basically, if you have good and weak, you want to neglect the weak.
I think it depends where the layer is. Because if the layer is at the bottom, I think the top players, because they're stronger, they will capture the load and they will not allow anything to go to that weak layer.
Correct. So it's also, I mean,
well, it is vice versa. I think you can let that layer to contribute.
Correct. So there are many rules like that, but it's all on what you just described. It's a lot of common sense engineering, right? So the important part to always understand is the load goes where it can be taken, right? So if you take a very competent rock at the top, all your load is gonna go there. It will never go to the embedding. So it will be conservative to neglect. But as you say, if the weak is at the top, then you can say, okay, well, that's gonna help, right? And then the bottom is gonna contribute. So there are a few rules of thumb here and there, like, for example, there is another one that if you have a recovery, like an RQD, an RQD for the recovery that is less than 20%, you typically neglect that layer if you have rock that has RQD greater than 80. But at the end of the day, it's just what you said. It's common sense of thinking where the load is going to be and making sure that you don't assign load to places that will never go.
I was just discussing similar things a couple of days ago with one of the experts, but not in Pennsylvania. He's in Atlanta, in Georgia.
Okay.
And he mentioned that their LRFD method that they're following is based on that summation I talked about. I'm not sure if I understood that correctly 100%, but we may come back to this in another recording. So if you have a couple of layers contributing to your resistance, it's like you calculate the resistance from each layer, then you apply a different factor based on the layer type, the installation type, the pile type. Then you sum the total factored resistances instead of summing all the ultimate resistancing and applying one factor at the top.
Yes, no, it's interesting because if you have the same factor resistance, then it's the same if you do it one way or the other, correct? Like if I have for all layers
the same, if you have the same factor,
yes,
that
is
will
the same.
But
if it's different, correct. So, and that also depends designer by designer. I tend to only rely like on the strong ones, right? Like on the strong layers. So I use the same resistance and I neglect the other ones. But for example, if you are doing a mix of soil and rock, then you will have different resistant factors. And then it will be more appropriate to do it the way you described, mathematically. However, I will not do it that way because I typically tend to neglect the layers that are weak because I know the load cannot go there.
I think we in Canada we follow the one factor method. So I calculate the total resistance
similar to the way I do
and
it.
apply the 0.6. I think in our
in your code.
In our manual is 0.6.
So I have to ask you. So I guess when you mentioned Atlanta, I imagine you were at Superpile, right?
I was,
and it probably was my good friend John Wolosuk from Keller Engineering. He always talks about drill shafts, and it's very entertaining. So I was right.
I don't want to say. I don't want to tell the names.
Keep the name, but I'll text him after our call. So
you text him and check with him, but he
exactly.
Maybe he knows about this. Yeah.
Yes. All right. Well, anyway, let's go back into
continue. And now we will leave this equation for a while. Yeah.
Correct. All right. So then the equations just require, I mean, if you are using this, it requires that you have to have a clean socket. You cannot have any smearing. You cannot have any weathering, any collapse. You cannot have, I mean, basically what the AASHTO, when you read AASHTO and LRFD, it basically is very strict and say you basically have to construct a good quality product, right? You have to have a good quality socket that is free of sediments that deposit in the socket and things like that. So the main line here is that the construction quality assurance and quality control is a critical item. That's the only way that you can apply this equation. So let's just do a quick review, very, very simple, of the drilling tools that we have now, because they also have evolved a lot, right? Not only the equations change, but the equipment also changes. So by no means I want to do a comprehensive review of drilling technology, But these days, this is kind
No,
of what we
let's
use.
have a look to your experience. It's nice.
Exactly. So on my experience, this is what you see. And obviously keep in mind, I'm not a contractor, right? I'm on designing, but I do also a lot of design build and I like to be involved in construction. So all these pictures that you are seeing come from my projects. So this is, probably the most useful tool. I mean, it's basically this drill goes down, it has separate rotating, blades, and then it cuts the rock, chew it. It's pretty good. We still use augers, and you can see a picture on the right, top right. Depending on the rock, a weak rock is going to be chewed by the auger with absolutely no problem. They come on all varieties of sizes, and I'm never claiming to be a tall person or anything like that, right? But I'm also not the shortest person, right? And when I stand next to one of these, you can see the scale, and you can imagine, how these things just go through rock and basically make the hole. So it's amazing. I mean, the equipment that we have these days can adapt. You can see there is kind of like a regular, almost like an excavator, right? And then you have these the attachments. There is different conditions. Sometimes you have projects that you are in a really easy access area. Sometimes, like this project, I'm standing there with all the engineers that we work together. In this case, we actually have to make a berm in order to make the drill shots, and the equipment have to pass in front of the newly constructed one to keep going. So it's an interesting setting. I like this picture in particular because it's a project that we did in downtown here in Pittsburgh, and you can see how, even though we are doing drill shafts, there is the limitation once we get close to that bridge that you don't have the clearance, right? If you are doing micropiles, you may have the clearance to go under the bridge and construct. But obviously, doing drill shafts, as obvious as it sounds, you have to keep in mind the environment that you are constructing on, because the constructability aspect is important, right? It's a big rig what you are using. And then another one, this picture in particular, what I like, it shows that rig, right? That auger can go through everything. And in this case, I know it looks kind of like mucky and it looks dirty, but in this case, we have alternating layers of coal and bedrock and coal again, and this thing can chew through everything. Uh, there is some environmental aspects, obviously, that you have to keep in mind, because when you are going through a lot of these materials and they got all mixed, may not be ideal. But I guess that's not what we're talking today. We're kind of just describing the power of the equipment, and it work on all kind of conditions. This one is doing drill shafts in the winter. So obviously you can see that even though the engineer that is smiling is completely freezing there, the equipment is doing fine, right? And they don't slow production or anything like that. So then from there, we basically did a step one, which is making a hole. Once we have the hole, then we need to keep the hole open while we continue drilling in bedrock, right? Typically, drill shafts have a different diameter. Like, you go with a diameter on soil, and then once you go into rock, you go with a different diameter. It tends to be smaller because the socket, you need to support the soil. So this is one of the main areas, and it's a main area of debate today, which is the use of casing or the use of the slurry or bentonite, right? For transportation projects, ASHTO, they typically require to use casing. They want physical casing basically to put this kind of, this kind of cylinder that maintains the hole open, right? And then once you have the soil open in soil, then you can drill bedrock and you can do your rock socket. Um, I'm sure, Ahmed, you have experience to, using bentonite and using polymer, which is another way to keep the hole open, right? And
Yeah,
and, and the idea is that you make the hole and you have the polymer or the slurry and you drill, but then you maintain the hole open without the need of this. I mean, obviously, everyone that sees that picture on the left, which, by the way, I have
well,
to make the parent.
we can't ignore having a casing. You should always have
Hmm.
a casing.
Hmm.
But how long is that casing? So if you have bentonite or another slurry or polymer, then you can shorten the casing that you're using. But if you don't have, then you need a long casing, of course.
Correct, and that is expensive. And right now, that's pretty much what is being required. Now, why I say that is a discussion, there are many points of view on this, right? So one point of view is saying, and unfortunately, this comes from the bentonite times, right? Bentonite, of course, is a clay and it expands and all that. And I guess the discussion was that when you have bentonite and you remove the bentonite and you put the concrete, you leave what is called the crust. And the crust is, or the cake, it's kind of what stays in touch with bedrock. And you are basically going to have bedrock, a bentonite residuum, and then the concrete. And that is your shear strength. So what is the good of design rock against concrete if in reality I have this bentonite cake that is left behind? However, that is long time gone. I mean, I don't think many people use bentonite like that anymore, right? It even has the environmental aspects of dealing with the bentonite. So we have great manufacturers that are doing polymers that are extremely capable, and some of them actually argue that the contact between polymer, rock, and concrete is even better than concrete and rock. So I do see a lot of future advancement on that area, but as of today, you are typically in most states required to use casing if you are doing LRFD design and if you are doing typical transportation projects. Private industry, a complete different animal, right? I mean, that's the reason that all these companies on polymers survive. But it's interesting. So for the purpose of today, we're gonna talk about casing because that's kind of what is required on LRFD design with Ashto. So the picture on the left, I'm very proud. It's man, I'm getting old, Ahmed. It's 16 years ago, and it was it was probably one of the biggest projects that I was doing early in my career. I was extremely proud. Looking at the casing being that size that I could almost, step inside. It was very interesting. The picture on the right, you can see this is actually the Allegheny River Bridge, and you can see the four casing being lower right into this, going into wreck and doing the I guess the socket of the bedrock. Then the next one, once we have the hole, once we have the casing, then we go and put the reinforcement. Uh, the reinforcement itself is just the regular design of a concrete column, right? So you have basically two designs. One is the axial design. I'm talking the structural aspect, right? And keep in mind, I'm not a structural engineer. I'm just describing the process from my point of view. So you have the axial design, which is the capacity of that, which is going to be the design of a column, right? You have concrete, you have steel, and then you also have to do a lateral design. In drill shafts, we do we use, for example, programs like RSPile, or we use programs like LPile, any program typically with PY cores, that gave us the reaction, right? So basically, I'm looking at bending, and I'm looking the reaction of the soil, and I'm looking the structural capacity and the stresses that I'm using with bending. So that is basically, in a nutshell, the design. I only do the geotech design, right? The structural engineer is the one that is going to do the structural design. Now, whoever end up doing the reinforcement on a drill shaft
Now,
typically is like,
in your company, you don't do the structural design for the piles.
For the piles. I mean, depending on the pile, like if it's a driven pile or a micro pile or something like that, I may just do the capacity if it's an easy structural design, right? If it's just like the strength of the concrete multiplied by the area of concrete, the yield of the steel multiplied by the area of steel, all times 0.85 or something like that. If it's a basic element, I do it. If it's axial, but obviously elements like this, I don't, because it has a lot of structural aspects of it. And I always keep true to myself. I always say every geotech engineer, it's a frustrated structural engineer, right? I think all of us at some point of our career when we started, we probably wanted to be structural engineers, and then we realized how complicated it was, and how predictable it was, and it was always the same equation as recipes. And then we found rock mechanics and soil mechanics, and then we shifted. So yeah, so I always know my boundaries on a structural engineer, and I have a lot of respect for structural engineers because they definitely know a lot more than we do in terms of
depends.
structural
It depends
capacity.
because you are in a consultancy.
Mm-hmm.
But if you are in a contractor side,
Mm-hmm.
and the job is a design and build job, so you will not interfere with the design as a consultant. So
Correct.
the contractor should have a competent engineer who can design geotechnically, and maybe another engineer or the same engineer to design structurally.
Correct. Correct.
We have just added the interaction diagrams and design of reinforcement in RSPile. If you
Really?
like,
Oh,
yeah,
that's awesome.
if
That's
you
pretty
like that,
cool.
yeah, if you like to see it, it's interesting now because you can check your results and check your capacity immediately. Yeah.
That's awesome. That's awesome to have all integrated, right? And I think those are the advances that really make, because even as a geotech engineer, and even if you are not doing the structural design and a structural designer is going to do it, you need to know the basic and fundamentals. And looking at these diagrams, you should be able to see if something is right or wrong, right? Even though you're not doing the final design,
Yeah,
it's
at least
important to have an idea.
you get satisfied with the design that is given to the
Correct.
pile.
Correct.
I
Correct.
want to ask another question here. This
Sure.
is what I see. It looks like it's a factory prepared cage.
It was actually not. It was ensemble on site. So it's just that the site kind of looked like a factory, but this is right next to the river.
It's very beautiful done,
Yes,
beautifully done. I mean,
and Ahmed, this picture to me is very controversial because it's in 2007, right? So I
yeah,
mean, we're talking that is 16 years ago. You can see me at the end of the tunnel or the end of the shaft on the left, right? I was so proud of this picture when I took it because obviously I identify with the project, right? So I
I
share
just
it in
I
social
just
media.
don't
Go
I
ahead, go
just
ahead.
don't like the spacing between the bars. It
Yes,
looks
well,
like there are locations that the concrete cannot flow through.
and we'll go into that in a second. But at the time that I took the picture, I shared it in social media and all that because I was extremely proud. And actually, at that time, we're talking 16 years ago, I got a lot of feedback from friends, and it's like, that's awesome. It's a beautiful picture and all that. But let me tell you what, that picture, if I took it today, I will absolutely not share it anywhere because this picture, as surprising as it sounds, has so many things that are wrong and so many things that today are unacceptable, right? So, for example, you pick on the spacing, right? I don't know how much the control is on that, but the main thing that has changed completely is the corrosion. I mean, look at the amount of corrosion that these pipes already have. It's not a severe corrosion, right? It's just a little bit of rust. This at that time, it was acceptable, and it was not only acceptable, it was almost encouraged. Like a lot of senior engineers, I remember learning from them, used to say it's good and it's desirable that you have a little bit of corrosion because that makes the bar a little rough, right? And
That
that roughness
that
interact with the
was
concrete.
exactly what I'm going to say to you.
Hmm.
I was
which
going
which
to
to be
say the
honest,
same thing. I know that a little bit corrosion, it's
it's
better for
good.
the.
And I completely agree with that. But if you say that today, it's absolutely unacceptable because
They
what
don't like it today. Okay.
they don't like it today. And what they want to see is this. Right now, when you design with code, you need to have corrosion protection. So now all my pictures pass from being rusty to being green, right? Because it's epoxy coated everywhere, right? So you can see this is obviously a more recent project. You can also see how the engineer changed in 16 years from the pictures, right? Because I'm still standing next to the cage. But now you can see, like all the river is covered in green, and that basically is the standard. You need the epoxy coating, which is just preventing corrosion. Now, I don't want to be controversial, but I still believe that the old school approach of saying that a little bit of rust has value, I don't think that is completely wrong. I don't think that those bars were completely shot by corrosion. I think it was just a superficial thing for a couple of days. But anyway, who am I to say what is right and wrong, right? So if we follow.
Come on, yeah. We are the people we should say what is right and what is wrong.
Yes, but
We,
the consensus in the industry these days,
it's not who writes a code.
correct, correct,
You need someone who has experienced the job
correct.
in the project site, in the
Hmm.
design, in the testing. It's a complete field of experience. Uh,
I agree.
I
I agree.
agree. I agree. Most of the people working in the codes and
Hmm.
authorities, they are also experienced, but usually we designers or contractors are more experienced than them.
Yes, and that's a really good effort. Like in the US, is happening. Like I have been involved. Like for example, I was the co-author of the LRFD design manual for the
Yeah,
state
that's
of Delaware,
important
right?
to join us with the
Correct.
authority engineers so that the codes will look more practical and more valuable. Uh,
Correct, and I think that effort is being made. So as I said, I was the co-author of the State of Delaware LRFD Bridge Design Manual for the geotech sections, right? And I know FHWA and ASHTO every day involve really good people that have been doing design and construction for years and incorporating. But anyway, going back into this, so the standard today is that you need corrosion protection. So you're gonna see that
yeah,
most of these are gonna be green. And there is also, which for good, that you could not see on the previous picture, but you see here, there is a lot of like white things, right? So you have like these little white balloons, or like they almost look like soccer balls that are like on the outside, right? And basically those are called centralizers, and it just maintain the cage in the middle. And then at the bottom, you see what is called the footing, which is basically a little footer for the bar. So when it goes and sit, it has some separation, and that allows for the cover. So I mean, definitely in the last 2 decades, it has been a good effort on corrosion protection and trying to make sure that these elements are better, right? So that's always good. But not always on a drill shaft. Your reinforcement is gonna be a bundle of bars. So I'm here with my companion of adventures, which is my son, right? He goes with me to almost every project site that I can go.
Yeah, you will
Um,
make this guy a geotechnical engineer, so.
hey, we'll see. We'll see. I say that my intent is that he's as passionate as I am to whatever profession he picks. If it's geotech, awesome. But even if it's not geotech, I'm cool as long as
Whatever
he
he
enjoys it.
likes,
Sorry, whatever he likes, exactly.
whatever he likes.
But it's just about being passionate and being committed and enjoying the profession, right? So, but anyway, so going back to the other part of the picture, it's not always the reinforcement has to be rebar, right? I mean, many times you can have, like in this case, for example, we have H piles, right? So you can have an H pile or you can have a W section. You can have basically a central element instead of having those. So these obviously are typically for like smaller loads, and they are for like drill shafts that also work as like soldier pad and lagging walls. So there is maybe different applications, but I always like to bring that into attention because people assume that it's always rebar, and it's not always, right?
Yeah.
All right, so then we go into an interesting part, and I think we were putting a lot of emphasis at the beginning that to use the LRFD equations, you need to make sure that you have good quality control. Now, what most people understand as quality control is the typical tests, right? So slump, entrapped air, some kind of density of the ground. But in reality, this also has shifted. It's way more than that, and we're going to cover in a second. But even the basic tests have changed a little bit. And it's a great point that you were mentioning before, that you said that the reinforcement appeared to be too close. One of the main problems that it was with the previous concrete mix, it was that sometimes it could not pass through the rebar. And another problem is that every time that you put concrete, we all know that you have to vibrate the concrete, right? And then you have to cure the concrete, so you have to make sure that you don't have like the cracking when it contracts. So
But you cannot
one
vibrate inside a port
correct.
file.
But then the problem is, how are you going to do that, right?
Yeah.
So I mean,
So
when
we
when
were using high slump values for that.
exactly, so they change, and now you basically use what is called a self-consolidating concrete, SCC, which is a really fancy name for a regular concrete with very small aggregate. And then the idea is that you are putting a material that you don't have to vibrate, because it basically just organizes by itself, it settles by itself. You don't have to vibrate it, it already has the density that it's supposed to, and then it hardens. And then the other big advancement, it's on all the additives that you can add to avoid the cracking when the curing is going on. Like when I started, sometimes they have a nightmare on drill shafts, which was like the refrigeration pipes. So it was basically pipes in the drill shaft that you just used to run water just to kind of, you know, avoid the scenario that you have a cooling that is too fast and it end up cracking the concrete. The self-consolidating concrete, the mixes that are now accepted or available everywhere, already take care of that. The concrete you don't have to be vibrated, and you don't have to worry about like the curing process. Now, we modified the tests to be able to kind of describe the problems that we were seeing. So for example, the slump test now is performed the opposite way that it was done. When we all learned the slump test, you put the cone like this, right? With the small part on top, the big part at the bottom. You put the different layers, you put the little rod just to make sure that the concrete kind of settles and accommodates. Then you used to take the cone out, and then you see how much it moved down, right? And that was your slump value. When you are doing drill shafts, the slump is referred not as that slump, is referred as a horizontal slump. So what you do is you do the same preparation with the inverted cone. Now it's exactly as is shown on the picture. The small part goes down. You put all the grout, you put all the concrete, then you lift it. And then once you lift it, you see how that spreads. And you measure the radius of that circle, of the resulting circle. And then you take that measurement, and then you do another one, putting this ring, this blue ring in the middle, that is supposed to recreate the rebar. And then you see what is the difference between the radius that you got, right, without the ring and with the ring. And they have to be within a tolerance. So typically it's about 1 inch. So what you're making sure is that the rebar is not negatively affecting the concrete and is not impeding the particles to pass through. So it's similar to the comment that you have before, Ahmed, which was, if the reinforcement ends up shifting or something like that, you want to make sure that it's not a problem for the shaft. Now, besides those typical testing, you still have like the entrapped air and different, like the densities and all that, which is kind of what I'm showing in the picture, that are always important to cover. However, those are not the ones that we are going to center today. We're going to talk about the new toys, and we're going to talk the more exciting testing that in reality now is required. It's almost a standard, or it is a standard, in order to use those equations. So for that, we go into two sets of tests. The first set is basically what we
Well,
do during construction.
that was very interesting. I
Mhm.
want to ask if that reinforcement
Mhm.
simulation, that
Yes.
one, the blue mold, and is it manufactured or welded just like what you're going to use, or this is a standard one?
No, it's a standard. It's a standard. And there is like an ASTM standard for that. So it tells you what is the separation that it has to be. So yeah, it's not going to be like project specific or anything like that. It's just going to be like a standard ring. Yeah.
Okay.
All right. So then let's go into the test that we do when we are constructing. And we're just going to talk about three basic ones. Uh, this is at the moment of constructing the shaft. Later, we're going to see some that are after you constructed the shaft. But when you are constructed, you basically have three. The first one, I'm calling it sonic caliper, but in reality, you can do it with radar, you can do it with laser. There is many companies that now offer this. But the idea is to do a 3D geometry as you construct. Then there is another one that we're going to call that is the mini seed, which is looking at the quality at the bottom of the shaft. And then we're going to talk about the downhole camera, which is one that gave us the quality on the sides. So we are trying to cover all aspects as we are constructing the shaft. So, but before we go into that, I always like to remember where we were before, right? I think when I started my career, and I'm sure the same for you, Ahmed, when we started our careers in drill shafts, we used to go inside the shaft. I mean, that was like the standard. This is
Yeah,
actually in a private
I,
project.
I never went into a shaft.
Oh man, I went to a good fair, and and
I
and,
was
and it,
always afraid of doing that, but
so yeah, but
thanks God, I never had that. Uh, I was never forced to do it. But we
so, but
used
most of
cameras.
us did. Most of us did, and at that time, it was exciting. But obviously, it's a claustrophobic experience. This is actually a recent one in a private project that it is exciting in the sense that you go down, right. And typically, you used to have a pocket pen, and the pocket pen was to test the side of the shaft, and then you go down, and with your feet, right, with your heel, with your boot, you kind of just make sure that the material was competent and it was what it was supposed to be. Obviously, these days, all this it's kind of not existing anymore, and unless you have like a small, private projects or something like that. But really, what we replace this is with the three tests that we were talking. So the first one is this, which is called the sonic caliper. Um, Again, I don't want to, show advertisement to one company or the other. I mean, this is one of the products. You have many products that do the same. And basically what you do is that you lower that element that you see on the picture on the right, top right, you lower it in the middle of the shaft, and this is creating like a 360 view. And as you go down, it creates a whole profile of what you have. So these days, when you construct these shafts, you know exactly what you constructed, right? You know the diameter that you constructed, you know if there is any undulations, if it was any caving or anything that was like that. So that's a first step. The second step is to look at the bottom. So for the bottom, we have this device that is called the mini seed. Some people call it mini seed because they say that it's
But
a.
you know the old. Well, it's not old. It's just it's still standard and used. The
Mhm.
tripod caliper uh,
Yes.
that we use for the diameter changes
Mhm.
uh, through the depth. I think.
Correct, correct. So it's basically the same, right? Like, what you're trying to establish is how the diameter changes as you go down.
But usually we don't do this for
Mhm.
all piles in the project. Are you doing it for all piles?
Yes, when we have like critical infrastructure projects, yes, every shaft has
Okay,
that,
it
and
makes
every
sense. So
and
for
every shaft the mini
example,
seed.
it's a bridge pier or
Correct.
abutments piles or something like that.
Correct. And that is also where LRFD comes into play, right? Because if you are doing critical infrastructure, obviously every element is important, right? I mean, there is redundancy, maybe redundancy, but it's like every element is critical. So typically these tests are done on every single one, right? Now I know it's not the same for example, in Colombia, where I was teaching last week, when I was covering all this, they said, oh, yeah, no, we only do, one every 10, one every 15.
No, if you have buildings and you have many piles,
Mm-hmm.
we usually do it like to test the machine. So if the machine, let's have 3 machines at site. So for each machine, you can try 3 piles. And if it's within the tolerances, then the machines are acceptable and the drilling is acceptable.
Correct. And that depends obviously on the redundancy of elements that you have on the project and the way that it was designed, right? So
Because this is very delaying test.
yes, no, absolutely.
A very delaying
Absolutely.
test. Yeah, it takes a lot of time.
Yeah. But like these days, when you follow AASHTO and LRFD for like transportation, then you are required to do it on every single one.
I understand, yeah.
So, okay, so then we move
What
into the
is
mini
mini
seed.
seed?
Yeah, so mini seed, some people define it as miniature submergible inspection device. When I learned it, it was miniature shaft inspection device. So I never knew which of the two meanings is right or wrong, but both make sense. But in reality, what it is, it's a very fancy inverted bucket. So what you have is you have what is equivalent to a bucket. Now, at the bottom, it has a hole with a camera, right? And then it has a hose, and the hose puts air, compressed air. So when you invert it and you lower it the way that is shown on the right, this goes down. You are looking what is on the camera, and because you have a bubble, because you have compressed air, that is creating a bubble, so the water doesn't go in as you go down. Now, when you are down, this is the way that you see it from below. So if you look at bottom up, you will see the camera that is there. You will see the air hoses, and then you're going to see these triangles, right? And you have 3 of those, and that triangle basically has some gauges. So the gauges, what it means is it's just giving you the depth. So when you put this on the ground, when you touch the bottom, the sediment that you have, right? Because you have like sediments that deposit from the water and different things, you are going to see how much sediment you have. If the sediment covers, for example, on this particular one, if the sediment covers the little red mark, then you know that you have a 1/4 inch. If it covers the green, you know that you have 1/2 inch of sediment. And then you keep going and going and going. So it's very interesting because it's a very physical way to measure, and everything you're doing is looking through that camera, right? But the principle is very simple. It's just to measure the sediment at the bottom. The way that you implement it is that when you have the drill shaft, you end up taking 5 measurements. You lower that bucket or the mini seed, you lower in the middle, right? You lower in the middle, and then you do north, south, east, west, and you just look on each of those gauges how much sediment you have. So, for example, what we have on the right on that circle is telling you that you have 1/4 of, a 1/4 of an inch of sediment on every reading. Depending on different specifications, you are going to have a different allowance of that sediment. The typical one right now, if you are using side friction and end bearing, most LRFD specs will tell you that you need 50% or lower with a maximum of 1/4 inch and a maximum sediment thickness at one location of 1/2 inch. So basically, a maximum value of 1/2 inch, and you need more than half of the readings with less than 1/4 inch, right? So if you are not using the end bearing, typically this relaxes, and you can have maximum of 1 inch and 50% or more of the readings less than 1/2 inch. So it's basically a way to control how much material can you allow. And I'm going to show you some pictures later on that are going to come back to this. And you're going to see the relevance. Why it's so important to control that sediment, right? Now, obviously, what we want is to have as little as possible, because we want to have the end bearing, the concrete, to be bearing completely on bedrock and not any kind of sediment, right? That's our point. All right, and then the last one that we have here is sorry.
How do you test the depth of the pile tip? Are you still using the old tape method?
No, so in this one we typically just use the depth, the initial depth. Typically with the sonic caliper, you know it, because when you lower it, you know what is the depth, right? If you were not using a sonic caliper, also you will just have like a tape as you just sound
You
it.
need to use the tape.
Yes, correct. But now on this one, like what you see on the picture on the left, what we're looking is like how much sediment we have, right? So on the picture on the left, I can see what color is being covered, and that's going to give me the thickness of sediment. I mean, keep in mind that this is obviously extremely important when you are working on a river environment or when you are
And
working
also
on.
it will give you a depth if you have a measure for how much
Yeah, you can also have it that way.
you
You can
push
also have
that
it that
one,
way.
right? Yeah.
Correct, correct. So that will be another way. So then what happened when you have sediment, right? This, for example, is in a project that we did in the Susquehanna River, that the bedrock was extremely fractured, and and even though we cleaned the shaft, just by the action of the water passing through, right, it was leaving sediments. So we struggled a lot because we used to do the mini seed, it was fine, then we waited a couple hours while they were putting things in, and then we did the mini seed again and realized that the sediment was accumulating very fast. So typically,
Although you have casing for
and
the
you
whole
have casing
depth
for the soil.
until you reach the bedrock. Yeah.
Yes, because in this case, the problem was that the water was coming through the bedrock, right? So
Yes.
you don't have casing on the bedrock. So it comes from the jointing on the bedrock and it was bringing sediments, and the sediment was depositing. So it was very challenging. Most specs require you to have to put concrete within like 2 hours after you do your mini seed. The spec is going to have a time limit that is basically saying once you say that it's clean, you are obligated to put the concrete, because otherwise you're going to start accumulating sediment again. So this project in particular was that the way that we clean it is with this shaft. It's like a small bucket, but it's basically like a ring, and it has a blade inclined, right? So when you go down and you rotate it, all that sediment end up being kind of like scrapped from the bottom, and you take it up. And that picture on the left
Yeah.
is basically that sediment coming out. Now, there is an interesting part of this picture, which is you can see the superintendent texting on his phone, right? And every time that I present this, people are thinking like, man, that guy is probably texting his girlfriend or his buddies or something like that. But in this case, it's the opposite. It's the coordination with the concrete plant, because since we were in such a time rush, right, that the moment that
Yeah.
is clean.
He's checking. Are you here at the site or not?
Exactly. Yeah. So in this case, this guy was actually like telling the plant and saying like, it just passed the mini seed or it has not passed the test. Don't send the concrete truck yet, right?
Oh.
So it's basically the critical coordination, just to make sure that, because I have had projects that unfortunately the concrete comes, but the mini seed has not been approved. And then while the concrete is waiting on the truck, we are still doing the mini seed and it's not passing, and they need to clean. And I have to waste concrete because by the time the mini seed passed, the mixer was on the site for too long, and the concrete was considered to not be of good quality. So it's a very interesting coordination that gets critical in some projects, and we need to make sure that that coordination happens. So, but anyway, so once you say that that's
And
fine,
also there is a delay that after the concrete arrives the site, you need to test the concrete as well. So
you need
that
to test the
also
concrete, and you need to put all the cage, right? You need to put all the rebar in the hole.
you need to put the
So
cage. You need to take
yeah, so it's a
for
time
concrete
sensitive
testing.
operation.
It's a very critical organization of operations.
Correct. So, okay, and then the third test that is supposed to be done during construction is the downhole camera. And the downhole camera is not any different than just a regular camera coming down, right? So you put it down on the hole, and what you're trying to look is the side, basically just to look the side of the rock socket to make sure that you have that roughness, right? To make sure that it's good quality. That picture,
Mm.
for example, on the left, in the right, it's a beautiful picture, right? You see that's exactly the rock socket that you want to have, right?
But this is already above water, right?
Yes, and that was the problem I was going to say. The typical problem that you have with this is when you are below water, not because of the water. If you are in clean water, you can have a perfect view. But typically you have like mucky water, you have like the sediments mix, and then at
Yeah.
that point you cannot see anything. So that's something that is important to keep in mind. Now, some people then go and say, well, if I'm going to have a stream environment, why I'm going to put in a specification that in a downhole camera? I also like to have the downhole camera on site for something that I'm going to show you later. That is a quality control check that I like to do. But it's always a good idea to have a downhole camera, even though when you are drilling, you cannot see much under the water.
Sebastian,
All
have
right,
a good
Ahmed,
day.
and everyone listening. Bye.
Bye bye. We need to go now. Bye.